What is going on, everybody? It is Kistner again, and today we are starting topic 3. Topic 3.1 is graphing polynomial functions. Now, topic 3 is all about polynomial functions. That's the actual title of it. Now, polynomials obviously are a bunch of single terms strung together with addition or subtraction. So we're going to get into some definitions here. Now, some of this will not be in your book, your notes, and some of this will be. But please just pay attention and listen as I get through these definitions that we need to know in order to do the examples that I am going to work with you out of your student companion. With that being said, you can turn to page 62. 62 in their book, okay? Page 62 will be where we start with our actual examples. But first, let's just get through some definitions. So writing a polynomial in standard form. So remember, a standard form of a quadratic was y equals ax squared plus bx plus c. And a quadratic is a polynomial. So we're going to have things like that. But here is the actual definition of a standard form of a polynomial. Standard form of a polynomial shows any like terms combined and the terms by degree in descending numerical order. Okay, so we have to combine like terms and get the degree in descending order. Okay, so for example, if we're looking at this polynomial, negative 4x plus 9 plus 2x cubed, this is not standard form. Not standard form. So let's talk about putting it in standard form. So we need to talk about this thing called the leading coefficient. Okay, you're going to hear me say that a lot. The leading coefficient. The leading coefficient refers to the non-zero factor that is multiplied by the greatest power of x. That's basically saying the coefficient with the highest exponent on the variable. So in this case, the leading coefficient is 2. Okay, in this case, the leading coefficient in this case will be 2. All right, so if we're going to start putting this in standard form, we're going to put 2x cubed first because that is the highest exponent. So my leading coefficient is 2. Okay. The degree of the polynomial you judge by the highest exponent as well. The degree of the polynomial is the greatest degree of any of the terms. This polynomial is the degree of 3, which will also be known as a cubic because you cube things when you raise it to the third power. And last, if we want to name this, we count how many terms. This thing has 3 terms, so 1, 2, 3. So this polynomial in standard form, so let me put it in standard form now. We put it in order, would be the leading coefficient, 2x cubed. It's called leading because it's out front. And we put them in descending order. Minus 4x plus 9, because my coefficients here actually go 1 and x to the 0 power here. Okay, so this is standard form of that polynomial. Decreasing order of your exponents as long as all of your terms have been combined. Like terms have been combined. All right, so let's actually put this one, and I don't know why there's 2 of these here. Let me unlock that and delete it. What is each polynomial in standard form, and what are the leading coefficient, the degree, and the number of terms of each? So we have 4 steps we have to do here. We have to put it in standard form and then name a lot of things. This should be example 1 in your book on page 62. So let's get right into it. Now, we need to put this in standard form first. We're going to put it in decreasing order. So I see negative 3x to the 4th is first. Okay, negative 3x to the 4th is the highest exponent that I see. And remember, the sign before the number stays with the number. And then the next one I see is this x cubed, so minus 5x cubed. And then it drops down to just an x, so plus 2x plus 6. So that's in descending order. Okay. The leading coefficient. Go ahead and write that out. The leading coefficient, you can just put coef. I don't know what that means. Coefficient is the number that's in front. It's negative 3 in this case. So once you put it in order. The degree is the highest exponent. In this case, it's 4. okay? And the number of terms would be 4 terms, because we have 1, 2, 3, 4 terms. They're separated by either an addition or subtraction sign. All right, I'm going to save part B for us to do in class. But that's all this looks like. That's example 1. Put it in order, label those 3 things, and we're done with it. So let's turn the page. And like I said, if you want to try B, you can go ahead and try it, but we'll do that in class with each other. Now this part's also not in your notes, so just listen to me. How do the sign of the leading coefficient and degree of a polynomial affect the end behavior of the graph? So end behavior is like where it would end. Like if you go to infinity or negative infinity on x, what does the graph look like? It's the end of the graph. So it's the behavior of the end behavior. So we have an odd degree, 1, 3, 5, 7, 9, 11. If that's your highest exponents, any odd number, the end behavior is similar to the linear parent function, f of x. As x goes to infinity, y goes to infinity. So as x goes out to the right, y is going out up. So we're going like this. And as x goes to negative infinity, this way, to the left here, y goes down. So an odd function would have a generic shape kind of like this, where it goes on forever that way and on forever that way. And that's probably not the best drawing. Let me do that again so you can show you that's going on forever. So it's going to go on forever this way and on forever that way. So as it goes out to negative infinity on the x-axis, it's going to go forever down. It's never going to come back up. And same thing over here, as it goes out right, it's going to go forever up. That is an odd function. Every odd function will have this generic shape. Now we might have functions that look like this. That's still an odd function. Doesn't matter how many humps it has in the middle of it. Okay? So let's get into even functions. Even functions, think about an even function. That's a quadratic. A quadratic is the smallest even function you can have, 2. And the end behavior is similar to the quadratic. Think of a parabola. A parabola looks like this, where your ends are going in the same direction. This one's going up, this one's going up. You can also have one that looks like that, where they're both going down. So even functions, you end up going even functions, you end up going the same directions, and odd functions, you end up going in opposite directions, your ends do. Okay, now once again, just like odd functions, even functions can have a bunch of different things. It could look like this. Oops, that last part didn't need to be there. It could look like that. That's still an even function. We know it's even because it's going down. Okay, it's going down. So I know that the highest exponent of this red function down here is going to be an even number. All right, so let's look at that as an example. Use the leading coefficient and the degree of the polynomial function to determine the end behavior of each graph. So first off, we need to check. I think this one is in order. It is in standard form because it goes 6, 5, 4, 3, 2, 1. So it is in decreasing order, 0. So the leading coefficient here is a positive 2. That's important. The positive is going to change things in a second. And it's even. Okay, and the degree is even. The degree is 6, which is even. So I know it's going to look where the ends are going up together or down together. So think about a parabola. What decided if it opened upward or downward? It was A, the leading coefficient. Same thing with every other polynomial. The first number will determine if it's opening upward or downward. If it's positive, it opens upward. So the leading coefficient, we're going to be opening upward, and our ends are going to both be going up and up. So what we would say here is the graph this is your answer. You should write down with me on example 2 in your book, or in example 2 in your student companion. The graph opens upward because the leading coefficient is positive as x goes to negative infinity. That was a horrible negative infinity. Y goes to negative infinity. Sorry, it goes to infinity. Erase that negative part of that. It goes to infinity. And as x goes to positive infinity, y goes to positive infinity. That's what it asks us to do. Okay. The first sentence describes the leading coefficient, and the end behavior is described by the second sentence. We'll do another one of those together in part B next time in class. So, graph a polynomial function. Consider the polynomial function f of x equals x to the fifth plus 18x squared plus 10x plus 1. Describe the key features of the graph in the box below. I didn't have a box here. And then use the pen tool to complete this table. So we're going to draw this thing. So, leading coefficient is positive. So we're going to say it opens. Well, actually, we can't say that on this one. It's not going to be flipped upside down. So we can't say anything about that. So what's going to happen here is as x goes to negative infinity, because the highest degree is odd, think about it. It's going to be going down this, like this. It's going to look something like that. I don't know where, but it's going to do something like that. So y goes to negative infinity. As x goes to positive infinity, y goes to positive infinity because it is an odd degree. Okay? Now, if the leading coefficient was negative, we would have flipped that around. It would look like this. It just flips the entire thing upside down. But we don't have that. So it's going to look something along the lines of this. Something. I don't know exactly what yet, but something like that. Okay? Now, let's talk about that. Now, it gives me this long table, and what I'm going to do is just use a calculator to plug in these points into this function. So what I'm going to do is I'm going to go to my calculator, go ahead and grab one, and I'm going to type in, let's start at -3. You don't have to plug them all in. Let's start at -5. Let's say -5, hit the caret right there, this little rooftop, to the fifth power, plus 18 -5 squared, just following along with the function here, plus 10 times -5, and it ends plus 1. So all I did was say x to the fifth plus 18x squared plus 10x plus 1, and I hit enter. And I get -2724. So that may not help me out much, but we'll see. I don't think I'm going to be able to graph that. All right. Well, let's move on down. Let's try -3. And what's nice about these calculators is if you just simply hit second, enter. I hit second and then enter. This whole thing comes back up, and I can go through and just change all the 5s to 3s. And I don't have to type in the whole function again. Change all the 5s to 3s, and I hit enter again, and there's -110. All right, so that's getting a little bit better. Getting a little bit closer. That should have been at -3. Hold on, let me move that. There we go. So let's actually try it at, let's try it at -2. Second, enter. I'll go through it all the way through this time. I hit it way too many times there. Okay, -2. And some of you may know a better way to do this, and that's fine if you do know it. I will show that to you guys later. But this is the old school way. You can do this with any type of calculator. It doesn't have to be a graphing calculator. You get 21. Okay? So if we continue to do this, just to speed up the video, if we continue to do this, you're going to get 21 there. You're going to get 8. You're going to get 1. Wonder where that comes from. That's your y-intercept right here. 1 would be 30. I've already done all these. 2 would be 125. And 3 would be 436. So let's pick out the points that I know I can plot. This only goes up to 30 and out to 6. So looks like -2 is the first point I can plot. -2, I'm at 21. So it's right in here. Okay? And remember, this is going down here. So at -3, I'm at down here at -110. So it's way down here. At -1, I'm at 8. At 0, I'm at 1. At 1, I'm all the way back up to 30. So something weird happened there. And 2, I'm way up here at 125. Let's just say it's way up there. Okay, and this one would have been way down here. So what it's going to look like is it's going to come from way down here, very, very steeply, bump around right here, come down, connect, and go all the way up there in those directions. That is an odd function. They're going in opposite directions, and it opens the way it should open. So really all we needed to draw was this part. You don't have to draw it off the graph. Put arrows on it saying it continues in those directions because it'll never bump around again, and we are done with that one. All right, so I'm going to do this next example in class with you. So this is going to be the end of the video. I hope you guys took notes. Go back and listen with sound on. Make sure it's important. Obviously, you wouldn't have heard me say that if you didn't have the sound on. But rewatch it if you have any questions. And I will see you guys next class. This is Kistner out.